Okay, so buffers are done. All right. It's good news because now it's all downhill from here. This stuff is really straightforward and really easy. Where students mess up in this unit in thermodynamics is in the little details, the units, sig figs, that kind of thing. So we need to pay attention to that. But there's not a lot of new concepts in thermodynamics, very similar to Unit 5, which was thermochemistry. So everything we did to enthalpy, you're going to be able to do and apply to entropy and free energy. So let's start and do a quick little review here. This is all stuff we've already had. And the first thing is talking about the first law of thermodynamics that states that energy cannot be created or destroyed. I do want you to know what the first law is. And today we're also going to talk about the second law. Because that energy that leaves the system goes to the surroundings, the energy that leaves the surroundings can go into a system, we say that when we add those up, because they're opposite, we get 0. So this is just the numeric or the equation way of representing the first law. Okay? This is a review. What was this? Big Mama. Correct. So this was Big Mama to solve for enthalpy. Okay? And we're going to use Big Mama again, but to solve for some different things. And a quick review of exothermic, delta H, enthalpy is negative. Endothermic, the delta H, endothermic, it's positive. And again, we're talking about surroundings on the outside, system on the inside. So when we talk about energy leaving or entering, we're talking about from the surroundings into the system and vice versa. We always are really focused on the system, though. Unlike physics, you do a lot of stuff from the surrounding in thermo there. Chemistry thermo is better than physics thermo. I'm just saying. That's going to get me in trouble. I'm sure one of you are going to run to your physics teachers and tell them I said that, which is fine. Whatever. I don't care. Okay. Let's move on. So what we're going to look at today is the second law of thermodynamics that says entropy of the universe will increase, meaning the universe tends toward disorder. So when I say delta S, I want you to use the term disorder, not order. That makes sense. Think about cleaning your room. How long does it stay perfect? Not very long. Never at all. So the universe tends toward disorder, and that's what entropy is. When we do Big Mama and we talk about equations, we're actually calculating the delta S, the entropy of a system. Okay? So if a system becomes more disordered or delta S increases, numerically we should get a positive value for that delta S. I need you to know that. A positive delta S means disorder is increasing in a system. A negative delta S means disorder is decreasing. Now we're going to talk a lot about the term spontaneity, and spontaneity is whether a reaction is going to happen or not without any outside influence. Well, one way to find spontaneity is through determining the delta S of the universe. Delta S of the universe is, if it's greater than 0, meaning positive, because the universe tends to disorder and because an increase in disorder is positive, a delta S of the universe that's positive is spontaneous. Okay? Kind of like that dirty room. That room getting dirty is going to happen, even though y'all are influencing it somewhat with your sloppiness. But to do that, you need not only the delta S of the system, you also need the delta S of the surroundings, which is another formula that we're going to have to memorize. But first off, let's focus on the system. When you find the delta S of the system, you get to use those thermo tables like you already know how to use them. And do what? What was this? What is that? Again, Big Mama. You get to apply Big Mama in the same exact way. I'm going to spell Mama differently that time. The same exact way as you did with enthalpy. Products minus reactants. The sum of multiplied by their coefficients. Y'all remember how to do Big Mama? All right. So if we ever need to find the delta H of a system, that's how you're going to do it. Delta H, I said. Delta S of the system, that's how we're going to do it. So how do we find the delta S of the surroundings? Go to the next page. The delta S of the surroundings is the delta H of the surroundings divided by T. That's not too hard to remember divided by T because when you look on the thermo tables, your units are always a unit of energy. Your unit of entropy is always a unit of energy. It's specifically joules per Kelvin. So we know delta H is joules, and divided by temperature gives you joules per Kelvin. So that's kind of a way that'll help you understand it. But here's the thing. When we used Big Mama on enthalpy, on delta H, what were we finding? Delta H of the what? The system. Whoa, they want delta H of the surroundings. So when we did Big Mama, we only know how to find delta H of the system. You guys don't know how to find delta H of the surroundings. Well, you actually do. If heat leaves the system, what did it do to the surroundings? It entered to the surroundings. If heat left the surroundings, it entered the system. So what's the relationship between the system and the surroundings? Negative. And so this is going to be equal to the same thing. And you know how to find that. Okay. So let me show you how the equation is broken down on the next page. This takes you through the derivation. So if we want to find if the universe is spontaneous, we need to solve for delta S of the universe. Okay? Yeah. So then we're going to take delta H of the system, delta S of the system. How are we going to solve for that one? Big Mama. And then we're going to take delta S of the surroundings, but we don't know how to find delta S of the surroundings. So instead, we're going to take delta H of the surroundings divided by T. But oh, I don't know how to find delta H of the surroundings, but I know it's opposite to delta H of the system. So that's this negative right here over T. So this is the way we come up with determining, using spontaneity, using entropy, whether or not this is going to be spontaneous. Spontaneous if delta S of the universe is positive. So we'll be doing a calculation with this in a little bit. Okay, but first, what I want to do are some simple dimple problems. I hope you all aren't disappointed. Today's lecture is really short. Is that okay? Aw, darn. Do you? I'll slow it down just for you. Okay, number one, they give us a little table up here. We're going to be using this for a couple problems throughout the in-class problems. It says calculate delta H for the following chemical reaction. How do I do it? Big Mama, using the data above. So Big Mama, my delta H of my reaction is equal to products times the coefficient. So 1 times, what's the delta H of AlCl3? Negative 704 kilojoules per mole. That's products. Minus, what are my reactants? Oh, they're all 0, aren't they? Because they're free elements. 1 times 0 plus 3/2 times 0. So my delta H of my reaction is equal to negative 704 kilojoules per mole. Whew! That was tough. That was review. Questions? One thing I want you to look at, you see the delta S, or the entropy of these guys? Not delta, but just the entropy. Are the free elements 0? Be careful. A lot of students assume that. Another thing you really have to be super duper duper careful. This is joules. This is kilojoules. We're going to be learning a combined equation tomorrow to find Gibbs free energy, where you're going to have to combine S and H. Can you combine them as they are on the table? No, you're going to have to make them both the same as each other. So again, units are really, really, really crucial in this chapter. That's free energy, and we're doing that mañana. So we'll talk about it tomorrow, okay? So right now, we're going to predict whether the entropy of the system increases, remains constant, or decreases when the following processes occur. Miss Nelson lent me her button that says stop entropy. So good luck with that. Ice melts. Now I want you to say disorder, not order. So ice melts. Is disorder increasing or decreasing when ice melts? Increasing. So what's the value of delta S of that reaction? positive, not the actual value, the sign. A precipitate forms. What happens to disorder when we make a solid from liquid? Disorder decreases, so what's our predicted sign? Negative. A solid dissolves in water. Disorder increases, positive. A gas condenses to a liquid. Disorder decreases, negative. I had Garrett this morning. Negatory, pository. Like, shut up. All right. So now we're going to calculate delta S for the following chemical reaction. What are we going to do? We did delta H for that one. We need delta S. What are we going to do? Big mama, but now we're going to use the delta S values in that table. And we're going to start where delta S of our system, our reaction, is equal to products 1 times 111 joules per mole Kelvin, products minus 1 times aluminum solid 28 joules per mole Kelvin, and I'm getting this from that little table, plus 3/2 times that Cl2 gas, which was 223 joules per mole K. All right, y'all, check my math. They got negative 252 joules per mole Kelvin. Yeah? So Big Mama, we can use Big Mama for delta H and delta S at any temperature, and I'm going to write that down. You can use Big Mama for delta H and delta S at any temperature. Delta H and delta S are not all that temperature dependent. So even though we collected these tables that are at the back of your notes, and the table we got information from was at standard temperature, which is what in thermo? 25, so 298. It doesn't change a lot with the fluctuation of temperature, so it's cool to use Big Mama for delta S and delta H all the time from the tables. Where we run into trouble is delta G. That free energy is very temperature dependent, so we can only use the tables if it's at 25. But again, we'll talk about that tomorrow. Number 4 is our last problem, but one thing I do want to do is show you how to predict what happens to reactions entropy when you look at an equation. So turn to page 10 in your notes, which is number 9. Where did my, there it is. Five, 6, 7, 8. I just want to look at these, and I want you to predict the sign of delta S looking at the states of matter. Because this is another way we can utilize equations. So look at the first one. In part A, we're going from a solid and a liquid to just a solid. What's happening to entropy? What's happening to disorder? It's decreasing. So if we were to calculate using Big Mama, we can expect the sign for A to be negative. What about B? Why positive? More moles of gas. If we had 1 mole of gas named Julian running around here in the room, it'd be pretty crazy, right? But what if we had 2 moles of gas? We added Jasmine into the mix, and they started all running around at the same time. Don't you think the disorder would increase? Absolutely. I wouldn't want to be in here. Positive, okay? I'm positive. I'm positive about that. Thanks. Thanks for that. And then part C, CO2 gas to liquid going to all gas. What's happening? Disorder is increasing because we're making more gas as molecules are spreading out, moving faster. So we also predict a positive. Before you do any math on any of these, I want you to predict, because those signs can easily get lost in Big Mama. And this is a gimme. I mean, you should know based on the states what's happening, so it'll be a double check for you. Okay, and you're going to see that happen in the problem that we're going to do. Number 3, let's go back and actually do that last problem. Then we're going to call it a day. Very exciting. What are we going to do? It's so exciting. We might have to play charadium. I did not say that on camera. This number 4 that we're doing, not number 3. No, I didn't. Yeah, I did. Okay. Consider the following reaction, and it's carried out at 100 degrees Celsius. Because it's at 100, and we're only dealing with, in this first part, entropy, we're okay with that. So we're going to calculate entropy using what? What equation? Big Mama. You guys have thermotables, nice pretty ones, at the back of this packet. So I want you to help me find some pieces of information. Remember, entropy's free elements are not 0, so we're actually going to have 3 numbers that we have to look up here. So we're going to start delta S is equal to, first is, yeah, I don't know if this number came out right. There's 2 ammonias. Is it 111? Or oh, I'm looking at the wrong problem. Where am I? Oh, there I am. 2 times 192.45. And this is joules per mole K. Okay, that's products minus reactants. So 1 times nitrogen gas, they got 191.61. Good. Joules per mole K, plus my other reactant of hydrogen gas, 130.684. Again, joules per mole. So when we solve, I'm going to move all this up and away. They got negative 199. Good. Negative 199 joules per mole. Now, I want to ask, is this prediction, would we have predicted this to be negative? Take a look at our states of matter. What are we going from? 4 moles of gas to 2, so disorder is decreasing, so we should have gotten a negative. Check. That's what I want you to do every time. Make sure it makes sense. All right, part B. It says calculate the change in entropy of the surroundings. Okay, we knew that surroundings is equal to negative delta H of the system divided by temperature. So let's go ahead, before we plug it in, as is, let's just find delta H of the system. Don't worry about this negative out here yet. So we're going to find how are we going to find delta H of the system? Big Mama, and we're going to use the table again. And I have all these written down, just double check. Delta H is equal to 2 times negative 46.11 kilojoules per mole, right? And then aren't all the reactants 0? Okay, so that's it right there. So that came out to be negative 92.22 kilojoules per mole. Well, I could plug that in there. But if you look at the next question, they're wanting us to find universe, right? So what would be helpful for me? I'm not done yet. I need to also divide by temperature, but what would be helpful for me if I'm finding universe? Change it to joules. And I can change this one to kilojoules or that one to joules, doesn't matter. I'm just going to go ahead and change this one to joules. But first, I got to divide it by the 100 degrees. What unit do you think I need to be in, though? Got to be in Kelvin. So I'm going to take negative 92.22 divided by 373. And that's going to give me, not, is it? Not, oh, well, okay, I wasn't going to do that part yet, but sure. Okay, we'll make it positive. We'll make it negative divided by 373. So that gives us 0.247. And then this is kilojoules per mole, Kelvin. So now I'm going to plug it in as joules down here and say that the delta S of the universe is equal to, what was our delta S of the system? Negative 199, right? Joules per mole Kelvin, plus 247 joules. Are you okay with the 1,000 little thing I did there? Converted this. And so what's my delta S of the universe? 48 joules per mole Kelvin. So is the reaction, is this a spontaneous reaction? Yes, because the delta S of the universe is positive. That's about as hard as this whole unit gets. Like, it's really not a hard unit at all. Like, we have 3 days to get through, like, 4 more pages of notes. Like, yeah, it is refreshing. I wanted you to have a little break after the buffers from hell. So you do need to practice your homework, though, so don't forget you still have homework.